Good morning or afternoon, Professor. We are Team P7, Team 2, and today we are presenting Recycling Pinball. Our focus today is not only to show that the game works, but to justify why each major design decision is the right one for this project. In part 1, we had good functionality but weaker explanation of architectural ownership during the demo. Today, we explicitly map visible behavior to responsible engine components. For every feature we show, we'll explain how it works and why we chose this approach over alternatives. We have 5 parts to this presentation. First, what changed from part 1? Second, how the 3-tier architecture separates concerns. Third, key implementation decisions including collision and event handling. Fourth, a live demo with explicit behavior to architecture mapping. And finally, testing results, trade-offs, and why these choices were justified. First, what changed from part 1? Looking back, we found 3 limitations in the engine. Those being scattered object creation, making consistency hard, inefficient collision checking that doesn't scale with more objects, and loose type safety and data handling. In part 2, we made 4 key upgrades to solve these. We introduced Scene Factory as a composition route to centralize how scenes and their dependencies are built. We added quad tree broad phase filtering, improving our collision scaling from ON squared to ON log n. We strengthened our contracts with interfaces and records for better type boundaries, and we built Pinball Event Bus to decouple gameplay policy from core collision physics. The reasoning is straightforward. One central composition path is easier to test, maintain, and understand for the next developer than scattered creation logic. These changes directly tackle the limitations we've identified, and they stayed realistic for our trimester timeframe. I'll now pass the time over to Isa to walk you through how our 3-tier architecture enforces these improvements at the structural level.
Hi, my name is Isa and I'll be talking about our architecture. Our architecture has 3 tiers. Tier 3 is application logic, where scenes, level flow, and scoring rules live. Tier 2 is engine core, manages entities, collision, scene framework. Tier 1 is platform adapter, where graphics, input, audio, and math wrappers are. The key boundary rule is that game logic should not directly depend on raw framework APIs. This is best as isolating framework dependencies give us clearer ownership and easier change management if rendering or input intervals evolve later. The most visible runtime behavior in this game is collision, so we now explain that ownership path. Collision Manager owns detection and physical resolution. It uses quad tree for broad phase, shape-specific collider checks for narrow phase, and minimum translation vector push-out for overlap resolution. Our colliders use double dispatch through iCollider contracts, so adding shape logic is extension friendly. We choose this approach as it avoids brittle runtime checks and keeps shape pair handling explicit and maintainable. When you see a collision response in the demo, here's what happens. First, the collision manager computes and resolves the overlap. Then, entity collision hooks apply the gameplay specific behavior. After collision is resolved physically, the game still needs to decide what the collision means.
Hi, I'm Jing and I'll be sharing more about our event-driven game policy. We chose to separate collision physics from gameplay policy via events. For example, when a piece of trash is hit, trash entity posts a trash collected event. The Pinball Event Bus then dispatches the event to Game Score Manager and Game Audio Manager, and the simulation scene handles the board updates. This structure enables policy changes such as scoring, sound rules, or extra effects to be added without modifying core collision internals. Next, we will cover how level content scales without turning into hard-coded scene logic. Levels are data-driven using base and specific JSON files, which are merged through data-driven level blueprint, which is then materialized by Board Builder into a board layout, and that is subsequently consumed by the simulation scene. This allows the balancing and progression to become content edits rather than Java rewrites, reducing risk and iteration time. This decision alone directly improved our development speed in our later levels. Now, we move to the live demo, where we will explicitly map each visible action to architecture ownership.
Hi, I'm Joseph and I'll be showcasing the demo. So let's just jump straight into the demo. When I click the Start Game button, this button click is handled in Menu Scene. This action invokes Scene Factory, Create Level, Select Scene, and Set Scene from Scene Manager. We use factory-based scene creation to keep our dependencies consistent and centralized. When I click any level button, level selection triggers data-driven level blueprints and creates simulation scene with injected managers. This justifies our composition decision because scene management is standardized and not scattered. When I click and drag down on the shooter rod, this handles drag input, The shooter entity also computes pull distance and posts a ball launch event. We support both drag and keyboard launch because accessibility is part of our requirements. For the flipper entity, the flipper entity applies rotational velocity and updates the OBB collider orientation, which affects the collision outcome. This produces skill-based timing control rather than random bounces. When a trash hits one target, the collision manager resolves overlap using MTB. Then trash entity on collision posts a trash collector event. And game score manager updates the score, while game audio manager plays the feedback audio. When I click escape, this is the pause overlay. It's handled by simulation scene and pushes pause overlay through scene manager stack. This demonstrates stack-based overlay control without destroying gameplay context. And lastly, what's the winning condition? It's to collect at least one piece of trash with all the balls. So on this, simulation scene pushes simulation result overlay with score and star feedback. This separates the end state UI policy from the core simulation update flow. You can see the other levels here, and here are the description visually. And you can also see the JSON data blueprints as well.
Hi, my name is Aung and I'll be explaining our testing strategy. Because a great pinball game relies heavily on feel and precise timing, a strictly automated approach was not going to be enough. We use a mixed approach, combining objective white box checks and Gradle verification with subjective black box playtesting. We are happy to report that all our core technical tests, which are things like high-speed collisions, spatial partitioning, flipper mechanics, are currently passing. We do want to be transparent about one gap. We haven't automated every single physics edge case. We acknowledged this early on and chose to mitigate this through controlled gameplay validation, rather than burning our timeline on exhaustive physics automation. This mindset also guided our three major architectural trade-offs. Firstly, we built targeted pinball physics instead of incorporating a full rigid body solver. A complete solver would simply be too complex and time-consuming for our module scope. Secondly, we use a scene factory instead of an external dependency injection framework. For a project of our size, explicit wiring was much cleaner and avoided unnecessary overhead. Thirdly, we use libGDX wrappers rather than rewriting custom math primitives from scratch. Attempting to rebuild mature math tools would bring a high risk of bugs with very little educational payoffs. Ultimately, these constraints were intentional and deliberate choices designed to maximize our maintainability, minimize risk, and guarantee a reliable delivery.
Hi, my name is Joel and I'll be talking about the innovation and OOP outcomes. So when we talk about innovation, we want to be clear, it's not just a recycling skin slapped onto a generic game. The innovation lives inside the architecture itself. For example, the state pattern is what allows our pinball entity to switch between idle, in-play, and dream behavior cleanly. You can see that in the state diagram on the right, factory pattern handles how scenes get created without the game logic needing to know the details. Builder helps us assemble levels in a scalable way, and observer paired with visitor style handling means our event system stays decoupled, so scoring policy doesn't get tangled up with collision effects. And the educational team, that's not separate from the engineering. Players have to use real-time and physics control to hit category-based targets, so the learning is built into the gameplay loop, not bolted on. With that in mind, let's wrap up with what we actually proved. To sum it up, we built a reusable layered engine with clear dependency control, made architectural choices we can defend with explicit trade-off analysis, and achieved full test suite coverage. But our real claim isn't just that the game works, it's that every major engineering decision is traceable, justified, and mapped to actually observed behavior. That's what makes this, in our view, a submission we are proud to defend. Thank you for listening.